So let's start the pig fitting. Here we will do that with the STO sample. We'll drag that into the plot section, and we get the different pages, the different core levels, titanium 2p, strontium 3d, oxygen 1s, carbon 1s, and we'll focus this time on strontium 3d. We can zoom in and out to get to the plot, and that can be done by keyboards or by zooming. So Control plus is one we can use, and maybe Control left or right to just move the plots. Okay. So now we will open the create model button. It is similar to Casa or Avantage. It is made of two tabs. The background tabs where you create the background, and the pig fitting where you will create the different pigs model. The methods available here are the linear, Shirley, smart, and multi-region smart. The smart, for people who use Avantage, they will know what it means. It means that we use a linear background when the background is going down, and we use a Shirley background when the background is going up. And if the background is higher than the data, then it will equal to the data. Let's use smart. Here we have offset, high and low, so that will create an offset at the end, or for low at the beginning. Here we will leave it to 0 for now, and this is the number of averaging points that used to be to decide where the intensity of the background will start. Okay, so now let's start creating a range. So we just click on one side, and if you're not happy with this, you can drag them like so. Yeah, and let's use the background so it looks like he created a Shirley background because he's going down. We may be pleased with the offset. We may want to see if this is good. So now I'm going to use Control down to zoom into the thing. Yeah, that was done correctly. But I may have wanted to go up to here. So, and maybe up to there. So let's just restart to show what we can do. Clear background. So I'm going to go up to there. Maybe let's try there, and let's see if it does it. And you see it doesn't. So I'm going to create an offset at high. So that may be around 500. So let's re-clear. Let's do a minus 500 in here as an offset. Minus 500 counts per second. And let's choose again the range around there. And it will be something like this. So this is just to get perfect background, but that's actually not needed. It's not even seen. So let's go now into the pig fitting tab. And here we have our fitting model and the different optimization methods. In the optimization methods, I really recommend to stick with least square. That works very well. And in the most complex, when let's say the method is stuck, you may just want to use the Kobila and then go back to the least square. The default with LMFit is this list SQ, which is similar, but this I found to work very well. So this is the number of fit iterations per loop. So it's going to fit 20 times, but in each of those 20 times, it's already going to fit 50 times. But he will, for 20 times, he's going to play with the constraints that we will use in this pig fitting parameter grid. So here the fitting models. So we have several possibilities here, but those are the preferred models. The default is for now the GL, but it is not my preferred one. The preferred one is the void function, especially if it's symmetric, and if it's asymmetric, the LA functions. There will be more models coming, especially the screwed void function, which is an asymmetric void, and that may become the preferred one. But I keep the GL and the SGL, which are known in CASA, as they are quick pick fitting, but they don't really fit well. For example, here, let's do an example. So I will use the GL, and I will create a doublet because it's strontium 3D. And the strontium 3D has two picks, which are split by a known amount. So there is a library inside the software, and this library knows what it should be. So let's add the doublet, and now we can see it creates two picks, pick A and pick B, where pick B is in function of pick A and in position by A plus the splitting I've been mentioning, 1.7, and this hashtag, which is plus minus in this case. So that is plus minus 0.2. So we let the program decide to go for better fit, to vary between 1.6 and 1.5 and 1.9. And then the width will be the same, and the shape, which is in CASA, for example, would be GL30. Here it is let to vary between 2% and 80%. Sometimes for GL especially, you may want to go to 90%, especially if it is a very sharp pick. And for the second pick, pick B, it is in function of pick A. And I can drag the pick as I wish, and I can select the pick using the Tab or Q button. So if I go Tab like this, I can just select between. And there is no way to select this one if I'm not selecting like this using the Tab. So now, if I choose the pick A and I move it, both picks will come. And I can go down, and both picks will go down because they are both links, or pick B is linked to pick A. So let's leave it like this and let it fit multiple times. So fit one times will go, instead of using a fit iteration of 20, it will just do a fit iteration of 1. So let's use the 20 times. And that is it. That is now fitted. And it looks pretty good. But when we zoom, so again, I will use the control down. When we zoom, we see it is not really well fitted because the GL is not very good for going down into the base. Okay, so let's try the other type of pick model. Let's remove the two. Okay, let me maybe zoom out completely. And now I will choose the SGL, let's say. And the SGL should be way better here, but sometimes, especially for sharp picks, it may over-exaggerate. So let's again add two picks. So they are both, pick B is in function of pick A. The width is in the same as pick A, and the area is also times 0.667. So you can decide to call it 0.667. We can divide by 1.5 also. 1.5. And here I like to leave a plus minus 0.05, so that gives a little bit of variation. Okay, so let's see now. So that will be exactly the same as before. And now we see it fits. Let's go into, we see the RSD is around 3.19, the residual standard deviation. And if we go down, we see that actually it's over exaggerating here, but it's quite a good fit. Okay. And now let's use my preferred, or let's use DLA for now. So DLA in this case is the same one as CASA. So it's an asymmetric Lorentzian, which is powered on the right side by gamma and on the left side by sigma. So if both values are equal, then it gives a symmetric peak. And in here, it kind of say what it is related to. So areas, because every every functions, every models we've done are in function of the area and not the height. So that's how we constrain the two peaks. And in here, we also have gamma, which is our right side, that we are going to vary, and we make sigma vary in function of gamma, and all together with this ratio here. So if this is sigma divided by gamma, but actually a concentration, so 50% will give that fully symmetric. So if we fix this, we get a fully symmetric peak. Okay, so now 2.7. So if it was 1, and I could try 1 will give a fully Lorentzian peak. But if you power the Lorentzian peak to a power 2.7, you get more and more towards Gaussian. It's not exactly Gaussian, so it's not a true peak, but it goes towards Gaussian. So in Casa, this is not, you cannot constrain that, you cannot vary this, you only vary inside the bracket. The software allows to vary this by itself. So now if we go fit multiple times, it's done, and he found a value of 3, and let's have a look on how good that fitted. So that is a better fit than the GL or the SGL ratio, and he found a gamma of 3 and a sigma of 3. And you can try this and on your Kalpha XPS, and you should find the same value, especially if you put the width of the Gaussian, which is the third numbers, to 0. So in this case, it is 0. It is grayed out, so meaning that it's not used, and it's only for information. I have here different models where I have the Gaussian done. This is this one here. So this is providing an LA convoluted with the Gaussian, so very similar to Casa. But this is a good fit. Let's try now with the void function. So the void function is now similar to Avantage, and that's actually the true fit. And I will add my two doublets, and let's go and see how it looks. Yeah, for now. And then if I fit this, and this is the ratio, the concentration between Lorentzian and Gaussian. In this case, we are down there now. And so we are looking at the width of the Gaussian and the width of Lorentzian, because when you work with void function, you cannot work with the full width, the overall full width. You have to work with the width of the Gaussian and the width of the Lorentzian. So in this case, I have to be able to work with the shape of the peak. I have constrained the width of the Lorentzian to the width of the Gaussian by this value here. So that's kind of 20%. So 20% Lorentzian. Okay. So now and this is going to be evolving between, or is going to be allowed to vary between 2 and 80 depending on how good the fit is. And then the second peak is constrained to the first peak. And so whatever value is here, it will go to the same value. So let's do that. And that's done now. And we can, so let me just change. So we got 25%, around 25%. And we got a width of 0.98, which is similar to all the other widths. And let's see how good it fitted. Sorry. So this is also a bit overshooting, but this is actually the true one. So that's the one I would trust more. And if you haven't noticed what was the width for the other pick, I will re-show you. So 0.98 is the width we get. So if I go to another model, let me go to the LA again, add the doublets and fit. And we got very, very similar widths. If I go now to the GL model and fit it, we get the one because it's not fitting properly. And if I go to the SGL model and fit it, we get also similar models. The area is also similar. So this is 10,000, around 10,500. And if I use the void function, add the doublet and fit it, and it fits way more, so it's getting 11,600. Okay, so now if I go to the next pick, let me just go up to see how good that fit. Yeah, this is the void. So now let's go to something a bit more complicated. So the titanium 2P. In here we would fit first the LA, and before I need to create a background somewhere around there, a background, and it looks, let's see how good it looks, and it's, yeah, well fitted. Okay, so now I will first fit a LA, and then I will fit a void function. So for a titanium 2P, the height is no more the same, and the width is wider for the titanium 2P 1/2 than the titanium 2P 3/2. So you cannot constrain the width together. You have to let it vary. So by just removing it, it will go to the default value, which is between 0.3 and 3.5. And if now I fit this, it's fitting quite well with the RSD of 2.36. But we can see that it fails here. And the reason it fails, to me, it's because LA is not a true pick. It should be a void function. So let's use now a void function, and let's do exactly the same. Let's add the doublet. Let's change, sorry, I've added the LA again. Let's add the void function, add the doublet, and let's avoid to vary the widths. So they should have different widths now, but the same, 0.5 area for the titanium 2P 1/2 in comparison to the titanium 2P 3/2. And now we have a very good fit, and it's fitting very well here. So that's the difference between the LA model and the void model. And if we just have a look at the overall shape, it looks quite good with the RSD now of 2.41. So I think it's better than what it was before. Let me show you now what LA would be good at. Let's go to the PT4F. So here you could put the VAMAS file, and it will create an Excel. So let me delete the Excel file. I will just add I'll just close that. I'll drop the VAMAS file into the plotlib. Now we get that file, and the Excel file is now created. As I explained in a previous video, this creates a page. So in this case, the Platinum the VAMAS file only have one core level, and then he provides an experimental description with all the information that is in the VAMAS file. So now for this one, we will use an asymmetric model, and that's the LA at the moment currently. So let's use again the pick model window. Let's create a background. So that's one. Let's see how it fits. That looks quite good, but again, this is quite difficult to fit for an LA. And we may want later on, and we will, change the background to around here to so-called fit better. Okay, so now let's add our pick model, and I will then explain why. So this is Platinum 4F. I've added, I have left the other models in here. So it's all removed. Let me just create that. And so now this is symmetric because we have 50%. And by default, the default value is 2.7. So let's change this to allow this asymmetry. So if we put hashtag here, instead of fixed hashtag 25, it will allow to vary between 25% to 75%. And because it's asymmetric on the left, then it will be below the 50%. So this will go lower, and this may go higher or lower depending on how it needs to fit this N shape. So let's happen, and that's done now. And we get an asymmetry of 30%. So this is now 0.79 to fit it, and this shape here has to be, the power has to be 1.79. So when I go down, so we can see an RSD of 1.82, but when I zoom down, I can see that I'm not fitting very well on the right side because it's an LA, and then I'm fitting quite well on the left side. So this is where I may want to change the background, let's say, because we can, and maybe add the background from here to there. Change, and then we refit. Obviously, this is not great, but it is possible. That's all I wanted to show. It's not wanted to do this. We may want to let it, so clear the background. Let's go maybe from here to there, background, and fit. But still we can see where it's failing, but this by eye is not really seen. Okay, so we get now an RSD of 1.66, which is quite good. So this is what the different type of model can do. We have, as I explained, different type of PIC models. For example, the LA convoluted with the Gaussian, and this is here. And I could just give a small introduction to this one. Let me go back to the STO. And again, to the strontium 3D. Let me fit something here. We know it's not going to fit too well, but that's fine. And now, if I use an LAG, so let's go to void to see what we need. So in here, we would need a width of Gaussian of 0.82. And that's the information that we can get to, and the rest is the width of the Lorentzian. So now if you think about of this type of function, then it is a Lorentzian that is, maybe not this one. Yes. So let me remove the pick. So now I have possibilities to play with the Gaussian, and I will decide to stay at 0.82. Because that's what I saw in my void. That's what I was going to get. So I'm going to fix this, and I will tell my gamma to stay at 1. Yeah, and I'm going to fix this also. And now this one is in function of pick A, so it will also go to 1. And because of my 50% here, then the sigma will also go to 1. And this is now becoming a true void model, but with the fixed width of Gaussian. So if I now fit this, yeah, and it looks very well fitted, and we have, okay, RSD 3.3, but if I go now down, it will look very similar to the Lorentzian, to the void function. And if I let it vary as well now, let it vary, and maybe even redo the whole lot. So I can drag the peak down. Let me just show you. I can drag the peak down and let it vary by itself by using the halt. So the halt you will be able to move the peak. So for example, if I go now to tab A, and I'm now constrained into pick A, I could move it, but I can also move it by keyboard. So now I will go down and move it somewhere here, and let's see if this will go to 1. So it's finding that it's very close to 1. Okay, I could change that to 2 or 3 just to show that it's possible. So now 2 or 3, maybe this one as well, and then let it just try to find the right number, and you see it always go back to 1. Okay, so that is LA when it becomes a true void function, because this is now 1.